This is Math 5700 Lecture 37, and today we will finish 6.1 and start 6.2, sections 6.1 and 6.2. Shall we get started? Okay, so I just want to remind you initially what we did, or at least part of what we did last time. So we had X and Y random variables. Let's say we're in the continuous case. We can look at the joint cumulative distribution function of the random variables. That's the function f of AB given by the probability that x is less than or equal to A, y is less than or equal to B. So that's called the joint cumulative distribution function. And we say that x and y are jointly continuous if there is a continuous if there is a function of two variables f of xy such that we can compute the f of AB as a double integral, minus infinity to A minus infinity to B of this function f of xy dx dy. And here this function is called, this function has a name. This is the joint PDF, the joint probability density function of x and y. Okay, so that's more or less what we did last time, and we did some examples. But I want to now focus on another example, and that will be it for this section 6.1. Okay. So the following is listed as example 1F in the text. And it goes like this. We have a function, f of xy, which is given a function of two variables, e to the minus x plus y, if x and y, the point xy lives in the first quadrant. So that's 0 less than x less than infinity, 0 less than y is less than infinity. And the value of the function is 0 otherwise. So this turns out to be a joint PDF. You can check that it's double integral over the whole plane as 1. So let's let x and y have this as its joint PDF function as a joint PDF. Suppose you have a pair of random variables with this function as its joint PDF. So now we can form a new random variable. Let me just use RV for random variable. So let's call it Z, which is x over y. Okay, so that's a new random variable. And then I want to compute. Let's find the CDF, continuous distribution function of Z. So that's not so hard to do, but it takes a little bit of work. So what is it? So the continuous distribution function of Z at a number A is the probability that Z is at most A, which is the same as the probability that x over y is at most A, which is the same as the probability that x is less than or equal to AY. Okay, so now I want A to be bigger than 0 because if A is less than 0, because we're in the first quadrant, the value would be 0. So I want a to be bigger than 0. Okay, so now let's consider the region that we're talking about here that we're going to be integrating over when we compute this. So this is a line that goes through we can look at the line of slope A that goes through the origin, 1 over A, slope 1 over A. So that would be the line y equals 1 over A times x, which is the same thing, or same thing as x equals AY. And the region x is less than or equal to AY is this region to the left of that line. So this is the region x is less than or equal to AY. So we're going to be integrating over that region. So therefore, we can actually form this, figure out what this is. We can figure out what this is in the following way. It's the double integral. Okay, so now how do you figure this out? You take a strip, take a little text, you take a little horizontal segment, and you have a point xy, and you can write this region as a type 2 region in the plane. So the x is going from 0 to AY, and y is greater than or equal to 0. So therefore, what is this? It's the integral from 0 to AY, integral from 0 to infinity of the function f of xy, the joint PDF, e to the minus x plus y dx dy. Okay, so now we have to compute this. So the way to compute this is to rewrite it as in the following way. This is just the standard Fubini theorem. Right. So this is the same thing as the integral from 0 to infinity of e to the minus y dy times the integral from 0 to AY of this is not being written correctly. Let me make some more room. Okay, I'm going to clear the space here. Okay, so this is our integral, and this is the same thing as the integral from 0 to infinity, 0 to AY, e to the minus x times e to the minus y dx dy. Okay, so that's what we have to integrate. So if we do the first integral with respect to, which is with respect to x, we get minus e, minus e to the minus x times e to the minus y, where x is being evaluated from x equals 0 to x equals AY. Then we have to integrate that result over the y variable. Okay, so what do you get? You're going to get the integral from 0 to infinity of what? Well, the e to the minus AY can come out, and what's left over is minus e to the minus AY. I've stuck that into this expression here, and then we have minus negative e to the minus 0, e to the 0, which is 1. So I'll just write that as 1. dy, and this is the same thing as the integral from 0 to infinity. Now I'm going to try to simplify this. Okay, so what is this? This is the same thing as e to the minus y minus e to the minus a plus 1 times y dy. And then lastly, we can integrate now. And what do we get? We get minus e to the minus y, and then plus 1 over a plus 1, e to the minus a plus 1 times y going from 0 to infinity. And we're going to need some more space here, so let me draw a vertical line and continue up at the top. So this stuff here, if we do the evaluation, is equal to what? Well, when you stick in infinity, since a is, since everything, the exponent is always negative, you're going to get a 0 coming out from the evaluation at infinity. And then when we evaluate at 0, you're going to get a negative 1 plus 1 over a plus 1. So the answer is 1 minus 1 over a plus 1. So we've concluded, so the conclusion is that f sub z of a is equal to 1 minus 1 over a plus 1, which is what we needed to do. That's what we're asking to do in the problem. So that's the answer. So, okay. Okay, so the last part of 6.1 considers many random variables, many RVs. So you have like a bunch of them, say x1, x2, etc., xr. And these are continuous random variables. And what you have is you can talk about the joint CDF in that case. It's just a generalization of what we did with n equals to r equals 2. So we have the probability that x1 is less than or equal to a1, x2 is less than or equal to a2, etc. xr is less than or equal to ar. Let me write n instead of r. Xn is less than or equal to an. That would be a multiple integral, dot, dot, dot. So it's going from minus infinity to a1, minus infinity a2, etc., minus infinity to a sub n. And then you would have some fx, there's a function f of x1 through xn, and then you're differentiating, you're integrating respect to dx1, dx2, etc., all the way up to dxn. So this is an n-fold integral. Okay, so you have a multiple integral, not just a double integral. It could be a triple integral. It's going to be a fourfold integral, depending upon how many variables you have. So this function here, that's in the integrand, is called the joint probability density function for the collection of random variables. And the book gives one example, which is that of the so-called the multinomial distribution. Which goes like this. Suppose you have an experiment. It's like a Bernoulli trial, but it's not flipping a coin. There's not two outcomes. You have more than two outcomes. Say R outcomes. For example, if I roll a die, that's an experiment with 6 outcomes if it's a 6-sided die. So example, a die roll. Okay, so then what we do is we have R outcomes, and each outcome, the jth outcome has probability P sub j. Since there are a total of R outcomes, the sum of P sub j goes from 1 to R, is equal to 1. Okay, so now let's let x sub j be so suppose we perform this experiment n times, okay? So perform the experiment n times. For example, roll a die n times. And let xj be the number of experiments in the n times that you've done the experiments which have outcome j. Okay, so that's what I want to look at here. This is an example of of now we have, what do we have? We have a bunch of different random variables. We have x1, x2, all the way up to, we have r random variable. We have a bunch of random variables. Okay. Yeah, so we have x1, x2. x1 is the number of times the experiment delivers you the first outcome. x2 is the number of times the experiment done n times delivers you to the second outcome. And then we have all the way up to xr. So we have r random continuous. We have r random variables, either continuous or discrete, depending upon the situation. Actually, it's a discrete random variable because it's a whole number. Okay, so these are discrete random variables. Okay, so now what I'd like to do is compute the distribution of these things jointly. So suppose we look at the probability that x1 is equal to n1. So in other words, the number of time the first type of outcome occurs of the experiment is n1 times when we do the experiment n times. Then x2 is n2, and then all the way up to xr equals nr. Now, since we're doing the experiment n times, the sum of the n sub j goes from 1 to r, is equal to n. All right, so now what is that probability? Well, what is that probability? Well, the probability of getting an outcome, the first outcome, was P1, and we've got, that's occurred N1 times, so it would be the contribution of P1 to the N1 from the first outcome. And then similarly from the second outcome, P2 to the N2, all the way up to PR to the NR. This is not the answer though. There's an extra factor in front of this. And the factor that goes in front of this is a multinomial coefficient, N1 through NR. So remember what that was. This N1 through NR is N factorial over N1 factorial and 2 factorial all the way up to N sub R factorial. Why is that? Well, the way I think of it is this. We have done the experiment n times. We have to put in n1 of the first outcomes in the n slots. So n1 of the n1 slots, there are n slots. N1 of the slots have the first outcome of the experiment. And 2 slots have the second outcome. So the number, etc., the number of ways you could do that, if you go back earlier in the course when we're counting, is this multinomial coefficient. So this is why this is the probability mass, the joint probability mass function of the experiment. In other words, this is P of N1 all the way up to N sub R is given by this formula over here. Okay. Okay, very good. So we're now done with 6.1. Okay, so 6.2 is about the notion of independence of random variables. So we'll say that x and y, which are random variables, are independent if we want to compute the probability that x is in A and y is in B, say, where A and B are subsets of the real numbers. This should be computed separately. That should be the same as the probability that x is in A and y is in B. So in particular, this is actually equivalent, it turns out, to saying that x is less than or equal to A, y is less than or equal to B. So that would be the cumulative distribution function being given by the probability that x is less than or equal to A times the probability that y is less than or equal to B. And that's if and only if, in just different notation, f of AB is f sub x, that's the marginal distribution function of x, times the marginal distribution of y for all AB, numbers AB. So this is really, this is actually the easiest way to remember the condition. We could also, in the discrete case, the condition is equivalent to saying that the joint probability mass function is given by the product of the marginal mass functions. And in the continuous case, everything is equivalent to the fact that the joint probability mass function is a product of the marginal mass functions. So you could either remember the cumulative condition or the non-cumulative version, which is this in the green box. Okay, so that's the definition of independence. And we should also note that the definitions will say that x and y are not independent, in other words, dependent, if x and y are not independent. Okay, so here's a stupid example, at least in the, not stupid, but toss a fair coin. Doesn't have to be fair, but let's let it be fair. 2n times. And let x be the number of heads occurring in the first n flips, and y be the number of heads occurring in the last n flips. There are 2 n flips, so there's the first n and the last n. So since these are independent experiments, the number of outcomes has nothing, these will be independent. These are independent random variables. So so that's probably as simple as it gets. So so there you go. All right. So the main thing I want to talk about is, right, for the rest of this lecture, we'll continue with 6.2 next time, is denoted by proposition 2.1 in the text. So, so the statement is this: if x and y are continuous random variables, then x and y are independent if and only if we can write f of xy as a product of two functions. In essence, we can separate the variables h of x times g of y for some functions h and g. So, so that's the, this is an if and only if. So, so I'm going to give you a proof of that. So here's the proof. So one direction is obvious, because if x and y are continuous and they're independent, then so if x and y are independent, we can set h of x equal to the marginal probability density function of x, and g of y to be the marginal density function of the variable y. So then we have f sub x, I'm sorry, that's not what I want to write. Then we have f of xy is given by f sub x of x times g sub y of y, which is equal to h of x times g of y. So that was easy, that direction. So let's go in the opposite direction. Okay, this is the hard part. So in the other direction, suppose we have the function f of xy is given by h of x times g of y. So then what do we know? We know the integral of from minus infinity to infinity, minus infinity to infinity. That's the integral over the plane of f of xy dx dy is 1. And we can rewrite this using the Fubini theorem as the integral from minus infinity to infinity of g of y dy times the integral from minus infinity to infinity h of x dx. Okay, so we can write this as a product of two numbers. Let's call the first number C1 and the second number C2. So this is C1 times C2, and its product is 1. Okay, so let's consider then what you get from that. Okay, so now let's consider, but f sub x of x is by definition the integral from minus infinity to plus infinity of f of xy dy, remember. And that's the same thing as the integral from minus infinity to infinity of h of x times g of y dy. And you can bring the h of x outside the integral because it's a function of x, not of y. And this becomes the same thing as h of x times the integral of g of y dy, which is the same thing as C1. Was it C1? No, it's C1 times h of x. Similarly, f sub y of y is C2 times g of y. But then, if that's the case, that implies that f sub x of x times g sub y of y, the product of the two functions is C1 h of x times c2 g of y. And the product of C1 and C2 is equal to 1, so this is h of x times g of y, but h of x times g of y is f of xy, and that's what we needed to show. We needed to show this equation held, and it does. The equation that's in the green box at the bottom, so the proof is done. Okay, so now what I'd like to do is I'd like to just do an example and be done with today. So here's a very quick example. Let's look at the example we looked at before. It's f of xy is e to the minus x plus y when x and y are in the first quadrant. So that's 0 less than or equal to x, or y is less than or equal to infinity. That's the first quadrant. So this is, and 0 otherwise. So then f of xy is given by e to the minus x times e to the minus y for x and y between 0 and infinity, and 0 otherwise. So let's let g of x be e to the minus x for x bigger than or equal to 0, and 0 for x less than 0, and let's h of y be the function e to the minus y for y bigger than 0, and 0 for y less than 0. So then if you do that, this becomes this, then f of xy is equal to g of x times h of y, and we're done. So that means that that the PDF of x and y have this joint PDF, then x and y are independent. Okay, that's it for today. So we are done for now.